Alright guys, we left off on this problem, so let's go through and look at these. Again, approach these as a puzzle. They're not meant to be difficult in any way, shape, or form. They just require a little bit of thought process. Okay, so the first reaction, this zinc and sulfur plus forming zinc sulfide, I'm going to leave exactly the way it sits, and the reason being is my zinc and my sulfur are both on my reactant side and in the right quantities. So I'm going to rewrite that down here. Okay, which means if I'm leaving this reaction alone, I'm also leaving my delta H alone as negative 183.92. Okay, my next reaction with this zinc sulfide, I want to get rid of my zinc sulfide in the first reaction because I notice it's not up in my original reaction. They're on opposite sides of the arrow, so I'm going to leave the reaction the way it sits, but the problem is I have 2 here and 1 here, which will not cancel out. Now I have 2 choices. I can double this first reaction, or I can half my second. I don't want to double the first because then my numbers won't match for my zinc and sulfur, so instead I'm going to half this reaction. So I end up with the arrow, first off, 3/2 oxygen plus my zinc sulfide. Over here, I'm going to end up with zinc oxide and sulfur dioxide, and that means I'm going to half this number. So I'm going to take negative 927.54, divide it by 2. I'm going to leave it as negative because we didn't flip the reaction, and I'm going to negative 463.77. Okay. My next reaction I'm also going to leave alone. The reason being is because I have my sulfur dioxide on the opposite side where I want it. Again, my problem is I have 1 here and 2 here, so I'm going to half that reaction as well. So I'm going to draw my arrow, and I'm going to end up with 1/2 oxygen plus sulfur dioxide going to sulfur trioxide. And that means I'm going to half my negative 196.04. I'm going to leave it the way it is in terms of sign, meaning it's going to stay negative. So I'm going to end up with negative 98.02. Okay. My last reaction, I'm also going to leave the way it is. Okay, and I'm actually going to leave it completely the way it is because it's in the right numeric value because I have my 1 sulfur trioxide, and they're on opposite sides of the arrow. So I'm going to be left with zinc oxide plus sulfur trioxide going to zinc sulfate, okay, which means my negative 230.32 is going to stay exactly the way it is. Okay, so down here, let's cancel everything out and see where we are. We have our zinc sulfates canceling out. We have our zinc oxides. I'm not sure why I put a 2 there. Jump back up here. Notice it's not there. Sorry about that. Zinc oxides canceling. Sulfur trioxides are going to cancel. Sulfur dioxides are going to cancel. And that should be everything we are able to cancel. So now we add up and see what we're left with. So we have 1 zinc. We have 1/8 sulfur. We have 3/2 plus 1/2 oxygen, which gives us 4/2, our 2 oxygens, going to zinc sulfate. Double check to make sure that's the original reaction, which it is. And now all we're going to do is take these 4 numbers and add them together. So negative 183.92 plus negative 463.77 plus negative 98.02 plus negative 230.32. Okay, and we're left with a delta H for the reaction of negative 976.03. So hopefully you got that. So that's the first way we can use Hess's law. Let's look at the second way we can use Hess's law. Okay. The second way is using something called standard enthalpies of formation. So what does that mean? Okay, that means some scientist somewhere sat in a laboratory and calculated the amount of energy it takes to form each individual substance. Okay, and their standard form, meaning to form water standard form, and that is assuming at 25 degrees Celsius, is a liquid. So how much energy does it take to take hydrogen and oxygen to form water? Same with ammonia, NH3, commonly a gas. Standard form is a gas. How much energy does it take nitrogen plus hydrogen to form NH3? And that list will be given to you, or at least the pieces that you need, and it's also in the back of your book. Okay, this symbol for standard is this degree right here. Okay, and then standard formation is this F down here. Okay, and of course that the 0 meaning standard is in standard conditions. Standard conditions are defined as these down here. Okay, which means gaseous substance are at 1 atm. Okay, also at 25 degrees Celsius. Pure substances are either in a solid or liquid form, or in a pure form, meaning pure substances as water being a liquid, it is strictly pure water. Okay, it does not have anything else mixed in with it. If we do have a solution, we assume that it's 1 molar, and of course it would be defined as aqueous versus as a solid or liquid. Okay, and then elements are in their standard state, meaning if they're diatomic, they're going to stay as a diatomic. And also that if oxygen is a gas, it's going to be a gas. If sodium's a solid, it's going to be a solid. Okay, so those are just our definitions of standard state. You don't need to memorize those or get caught up on those. Just understand that that's what standard means. Now, how much energy does it take to make oxygen into a gas? Well, it already is a gas. So the standard heat of formation, or the amount of energy it takes to form an element in their standard state, is automatically known as 0. Okay, so kind of keep that in your mind. Oxygen is already a gas. It remains a gas. It takes no energy to turn it into a gas. Now, how much energy does it take to take from oxygen gas to oxygen liquid? That would have a delta H. So in an element in its standard form, sodium being a solid, oxygen O2 being a gas, copper being a solid, bromine being a liquid, so on and so forth, those will always have 0, and that is something you need to know. Okay, so let's look at how we use this. It's actually not much different than what we just did, or at least in the sense of where it came from is not much different than what we just did. Okay. Okay, so let's say we were given a series of reactions and we had an original reaction. What would we do? We would rearrange that reaction and add up our delta H's and go from there. It's really the same idea, except we simplify it a little bit. Instead of given reactions, we're just given the substance. And then these are our standard enthalpy reactions, by the way. So nitrogen plus oxygen forming NO2 in its standard state has a specific enthalpy. Carbon plus hydrogen plus oxygen, all in their standard states, forming methanol, would have that much energy. Okay, and then oxygen, pure oxygen formation would have a delta H of formation of 0. Okay, just so we have an idea of that. From there, we could add these reactions up, get our delta H's just like we've always did. Okay, but we've got a simpler version of this. Okay, instead of having to do that, let's say we're given a reaction, we're given the standard enthalpies of formation. All we have to do is plug everything into this equation, which would add up to what we were doing originally. So think about it this way. CH4, if I was giving you the reaction formation, it would be carbon plus hydrogen forming CH4. Okay, all in their standard form. Okay, and we'd have a delta H of 75 for it. Okay, let me rewrite that, sorry. Delta H would equal negative 75. Okay, let's say I was doing it for CO2. It would be carbon plus oxygen forming CO2. And it would have a delta H of negative 394. Okay, now, for this reaction, I would want to flip it. Why? I would want CH4 on this side. I would want it on the reactant side, which would make this a positive 75. For this reaction, I'd want to leave it alone, leaving it as a negative 394 to keep carbon dioxide on this side. Well, look what this reaction does, or this equation does. We go from products minus reactants, which means our reactants at a negative 75 would go in here as a negative 75, and this negative, subtracting a negative, is the same thing as adding a positive. So we would end up with positive 75, just like we would if we rearranged the reaction. So it's really the same exact thing we were doing, except now we're not having to rearrange reactions or anything. We just have to take the numbers, plug and chug, and get our numbers from there. Okay, so let's look at these numbers and actually see what we can do. First and foremost, we have our little reaction down here. Methane is combusting. We have our delta H's, okay, and this is very similar to our equation that we used with bond energy, but notice this is products minus reactants. It's the sum of all the products plus the sum of all the reactants, and all we have to do is grab these numbers and throw them into our equation. So delta H of our reaction is going to equal products, and our products are carbon dioxide, so we're going to come down here and grab it. There's one of the carbon dioxides, balanced chemical equation, so 1 times negative 394. Plus 2 waters, 2 times negative 286. Okay, all that's going to be added together and subtracted from our products, or sorry, from our reactants, which I'm going to enter down, which is CH4, so 1 times negative 75, plus, wait a minute, there's no oxygen down here. Why? It's an element and it's standard form, so plus 2 times 0, which I know is kind of odd to think about, but I did want to show you it. All right, so now we do our calculations. So we have negative 394 plus 2 times negative 286, okay? And that's going to add up to negative 966. Okay, we're subtracting that from 1 times negative 75 plus 2 times 0, which is just going to give us a negative 75. Okay, and now we're just going to add a positive 75 to our negative 966. And we're left with a delta H of reaction to equal negative 891. Now, some of you are probably thinking, well, why didn't we just do this in the first place? Why did we do all the reaction rearrangement? Well, it depends on what I give you, or what College Board gives you, or what you're given in the problem. If you're given standard heats of formation, yeah, sure, you can just plug it into this equation and go. But if you're given reactions, guess what? You get to rearrange the reactions. Okay, let's keep going. Let's look at a couple more of these. Here's another one. What I want you to do is pause, go through and do your calculations, and make sure you're able to get the same number I get. Okay, so what do? We have delta H, which is always products minus reactants, okay? And that's very important to remember. If you forget, it is on your formula sheet. Remember, bond energy is the reverse. It's reactants minus products, and that's just because, again, the perspective we are looking at. So in this case, products minus reactants. So my first product is NO2, and I have 4 of them. So NO2 is a positive 34. Okay. And I'm going to get rid of that. Plus 6 times H2O as a liquid, which is negative 286. There we go. We are subtracting that from our reactants, which is 4 times NH3, which is negative 46. Okay, plus 7 times oxygen, which is an element in its standard form, so 0. So 4 times 34 plus 6 times negative 286. And really the hardest part of this type of problem is making sure you plug it into your calculator correctly. And I get negative 1,580. Subtract that from 4 times negative 46, which is a negative 184. So now we basically just add negative 1580 plus 184, and we get a delta H of reaction, as long as I typed everything into my calculator correctly, as a negative 1396 kilojoules per mole. Okay, let's see if we got one more in here. Okay, and we do. So try this guy, last one. All right, now let's go through and do it. We have aluminum oxide, which is 1 times negative 11676, plus iron, which is in its standard form. So notice he's not going to be over here, so 2 times 0. That is our products, minus our reactants, which aluminum is in its standard form, so 1 times 0, plus iron oxide, which is aluminum oxide, which is negative 16... Nope, sorry, iron oxide. Looking at the wrong thing. Negative 826. Okay, so now we just go through and do our math. So we have negative 1676 minus negative 826. Okay, and we do that math and actually get that number. And we get negative 850 for the overall reaction. Okay, so hopefully we're doing okay on this. What I want you to do is you can go through and complete some more of these if you want. I'm not too concerned about it because it's pretty straightforward. What I've done is I've pulled out a College Board problem, a free response problem, and we're going to work through this in the next video. What I want you to do is I want you to go through and see how you do on your own. Try to do all of it on your own, and then we're going to go over it, okay?